Hello and welcome back. In this lecture, we're going to solve some hard problems on polynomials. And as I mentioned previously, you can skip this part if and skipping this part doesn't really hurt the progress of learning. But these are interesting questions, and I'm going to solve them in this lecture. So I have them in another file. Alright, so the first question is find a and b. So a and b are some numbers or parameters such that the polynomial ax5 plus bx4 plus x squared minus x minus 1 is divisible or is divided by x minus 1, and its remainder on x plus 2 is negative 1. Alright, so let's call this p of x, and what the problem is telling us that if I divide p of x by x minus 1, the remainder is 0, right? So x minus 1 is a factor of p of x. And again, since the degree of x minus 1 is 1, the degree of the remainder r of x, so r of x should be a number, i.e. a polynomial of degree 0, right? And we already know that if I plug x equals 1 in this identity p1, it becomes the r, which is 0, right? So the remainder is given, and therefore p of 1 is 0. So what is p of 1? It's a p of 1 is a plus b plus 1 minus 1 minus 1, and it becomes a plus b minus 1. Therefore, the first information that we extract from the problem is that a plus b is equal to 1. Okay? And then the problem also tells us that if I take p of x and divide it by x plus 2, I get some quotient, let's call it q bar, plus some remainder, r of x. And the problem is telling us that r of x is negative 1, right? And we expect it to be a number because x plus 2, the degree of x plus 2 is actually 1, and therefore the degree of remainder must be between 0 or less than the degree of the x plus 2. So it has to be 0. It has to be 0 because the degree of x plus 2 is 1. And we already know that the p of, if I plug in the root of this x plus 2, which is negative 2, this is equal to r negative 2, right? And this should be a number r, which is negative 1. Therefore, the second information is p of negative 2 is minus 1. And if you plug in minus 2, a minus 2 to the 5th plus b minus 2 to the 4th plus 4 minus minus 2 minus 1 should be negative 1, right? So negative 1 cancels out. This becomes plus 6. And we have 0 on the right side. So 32a minus 32a plus 16b is equal to negative 6. And we can divide by 2 minus 16a plus 8b, okay, is negative 3, and divide by negative and then multiply by minus 1 over 8. So 2a minus b is 3 over 8. So this is the second information. And now we already know that a plus b is also 1. So just sum them together, add them together, and then 3a becomes 3 over 8 plus 1, which is 11 over 8. And therefore a is 11 over 24. So this is a. And what is b? B is simply 1 minus a. 24 minus 11 over 24. Therefore b is 13/24. Okay. All right. The second question, what is the least significant digit of 7 to the 1377th power? So first of all, 7 is an integer number, right? And therefore, when we raise it to some power, some integer power, the result is also some integer number. And if you look at let's say we have a general integer number that has n digits. Okay, let's call it a sub n, a sub n minus 1, a sub 2, a sub 1, a sub 0. I'm going to put a bar on top of it to show that this is not multiplication of these an's. This is just a number representation, and each one of these a sub i's is one digit. Okay, and we already know that when we talk about numbers, it's a decimal number, which means the base here is base 10. So if I expand this becomes an 10 to the n plus an minus 1, 10 to the n minus 1, plus a1 times 10 plus a0, right? So this acts like a polynomial p of x, where we substitute x equals 10. Okay? Now, if we think about the number, an integer number, as this representation, then a0 is called the least significant digit, least significant digit. And obviously, as you can probably guess, a sub n is called the most significant digit. Okay, and this is true for any base. For example, if so x equals 10 is basically base 10, but let's say you're working with computers and computers only understand binaries, so in computers you substitute a2 or base 2. Okay, but so this base 2 is mostly for computers, or when you're looking or working with binary numbers, zeros and ones. But in base 10, each digit ai can go from 0, 1, 2 all the way to 9. Obviously, the most significant digit, we assume that it's not 0, right? So a0, the least significant digit, sometimes the abbreviation is LSD and MSD. Okay? Now, when the problem is asking, okay, a is 7 to the power of 1377, okay, and then it says, okay, if I write this in this an minus 1 all the way to a0, what is a0? Okay, now obviously what you see that a0 is the remainder of dividing a by 10, because if I divide a by 10, it becomes an 10 to the n minus 1 all the way to a1 plus a0 over 10, and this is not integer, right? This is not integer, and therefore the remainder of a over 10 is basically a0 over a0, right? And so what we need to do, we need to calculate the remainder of 7 to the 1377 divided by 10. How do we calculate the remainder? And the way we're going to do it, we're going to assume that, okay, if you recall, we call this is a polynomial at x equal 10, and our polynomial px is basically an x to the n plus an minus 1 x to the n minus 1 all the way to a1x plus a0, right? And an minus 1 to a1 a0 are the digits. These are the digits, right, of this number 7 to the 1377, and we want to divide this by 10. So x minus 10 times some qx plus some remainder r, which is, we already know that this is going to be a0. Okay, all right. So if you know 7 divided by 10, the remainder is so if I take 7 and divide it by 10, the remainder is 7. If I take 7 to the second power divided by 10, the remainder is basically 9 or -1. Okay, if I take the 7 to the third power divided by 10, the remainder is 3. Okay, and if I basically, as I multiply by 7, the remainders also multiply by 7, right? And then I take only the least significant digit. And 7 to the 4 divided by 10, the remainder is 21, so 1. Now the good thing here is that if 7 to the 4 is 1, 1 is important, because then multiply by 7 to the 4, 7 to the 8 divided by 10, it's okay, and we go all the way to 1377 divided by 4. So 1377, if I divide it by 4, 3, 12, 1, 17, 4, 16, 1, 17, 4, 16, 1. So I'll go all the way to basically 7 to the 4 to 3, 4, 4 divided by 10. This also, the remainder is 1. And then multiply by 7 again. I realize that the 7 to the 1377 divided by 10, the remainder is 7. Okay? All right, the third question. Prove that a plus b plus c is a factor of a cubed plus b cubed plus c cubed minus 3abc. Okay, so let's say I call the a or maybe something like a capital X, a cubed plus b cubed plus c cubed minus 3abc. We want to show that this one has a factor of a plus b plus c. So a plus b plus c times another polynomial, q, let's call it q. This is another polynomial in terms of a and b and c. And yeah, so how do we do this? There are a couple of ways. One is method 1 is to try to factorize x. Basically, we start from the left hand side, which was x, a cubed plus b cubed plus c cubed minus 3abc, and try to see how we can factorize this. So a cubed, and remember, we have to try to take out something like a plus b plus c, right? So the way we can do this is we start by a plus b plus c cubed, and this is equal to the a cubed plus b cubed plus c cubed plus how do we calculate this? Let's see, we can just write this as a plus b cubed plus c cubed plus 3a plus b times c, a plus b plus c, right? So basically I thought of a plus b plus c as a plus b as a factor and c another factor, right? And now we have an a plus b plus c out, and this is good. But what is what is a plus b cubed? So this is equal to a cubed plus b cubed plus 3ab a plus b plus c cubed plus 3a plus b c a plus b plus c, right? All right, so what are we looking for? We're looking for a cubed plus b cubed plus c cubed minus 3abc. So our x, which was a cubed plus b cubed plus c cubed minus 3abc, is equal to basically a plus b plus c cubed, which already has a plus b plus c, minus 3a plus b times c times a plus b plus c. Okay, this one also has an a plus b plus c, minus 3 ab a plus b, okay, minus 3abc. So this 3abc comes from the original expression that we're looking for. It doesn't come from this identity, okay? And obviously the first term, and then if you look at these two terms and factor the minus 3ab, we end up with a plus b plus c, okay? And then we can factor 1ab plus c out. We end up with a plus b plus c squared minus 3a plus b times c minus 3ab. So basically our x, which is a cubed plus b cubed plus c cubed, a cubed plus b cubed plus c cubed minus 3abc, is equal to a plus b plus c times a squared plus b squared plus c squared. 2ab minus 3ab is minus ab minus ac minus bc, okay? And remember, this is an identity, which means it holds true for any three ABC numbers, real numbers, complex numbers. But this was a brute force way of writing things down and trying to factorize it. But there is a very clever way, so let's call it method 2, which we can take advantage of our knowledge, our knowledge of polynomials. And if you recall, I have used this trick before. So instead of so we can assume that one of a, b, and c are completely arbitrary. Could be a number, right? So let's assume that one of these is a parameter or variable x. So let's define a polynomial x cubed. So I'm going to take a as the variable, minus 3bc x, okay, plus b cubed plus c cubed, okay. So I substituted a with x. Now I wanna prove, if I prove that this has a factor of x minus b plus c, or x plus b plus c, then basically I show that this polynomial has a factor of x plus b plus c. Then I just simply substitute x with a, and then I prove the original problem, right? So let's call it a small q. So in order to prove that, I'm going to put a question mark or prove this. Again, q, the degree of q of x is 1. Therefore, if there is a remainder, it has to have a degree of 0, right? Therefore, the remainder should be a number, a constant number, and we already know how to calculate this. You take the root of, you evaluate the p at root of qx, p at minus b plus c, okay? So all I have to do is evaluate p of x at minus b plus c, which becomes minus b plus c cubed plus b cubed plus c cubed plus 3bc b plus c, right? And this is exactly the definition of b plus c cubed. So this is definitely always 0, right? And this means that my px, the remainder of px over x plus b plus c is 0. So p of x always has a factor of x plus b plus c. So just substitute x with a, right? Because x could be any number. Therefore, p of a cubed plus b cubed plus c cubed minus 3abc, has a factor of a plus b plus c. Done. Okay? So this is just using our knowledge of polynomials and the division and the fact that if q of x, the degree is 1, then the remainder should always be a constant number, and we know how to calculate that constant number. Alright, question 4. If x plus 1 over x is a, find x7 plus 1 over x7. Now the interesting thing here is that if I assume x is some variable u and 1 over x is some variable of v, these two are not independent, right? U times v is 1. And again, this is a symmetric expression. And this is also a symmetric expression. So I should be able to write this in terms of u and v. So this is u to the 7 plus v to the 7. Okay? And the way we're going to do this is basically we have to take advantage of the fact that u times v is equal to 1. Okay? So the way we're going to do this is we have 7th power here. So let's see. So what is u7 plus v7? First of all, u7 plus v7 has a factor of u plus v, right? We already discussed this because if I assume that u is a variable, then p of u is u7 plus v7, right? If I write it in terms of u plus v, some qu plus r of u, right? Then degree of the degree here is 1, therefore the degree of remainder is 0, and therefore the remainder is a constant number, which I have to evaluate it at u equal negative v, which is negative v to the 7 plus v to the 7 is equal to 0. So u7 plus v7 has a factor of u plus v, right? So all we need to do is write it down. u7 plus v7 is equal u plus v. This is like a polynomial division. Our variable we're assuming is u. So u is assumed here to be our variable of the polynomial. So if I divide the highest degree u7 divided by u, I end up with u6, and then you multiply by this u7 plus vu6 and subtract it from the whole thing is v7. I end up with minus u6v plus v7. So I end up with vu5 plus v squared u4 minus v cubed u3 plus v4 u2 minus v5 u plus v6. Okay? So the terms here, the general way to writing this down is that each term, it's something of u to the some power m v to 6 minus m, and 6 is 1 degree less than the power that we had here. Okay? This is 7 minus 1. And the reason is obvious, because all of these all of these terms have to have a power of 6, so that we multiply them by u or v, they give us u7 v7. And the fact that the sign alternates between plus and minus helps us to cancel out all the other terms. So whatever remains eventually is u7 plus v7. Okay. Okay. So what we're going to see here is that u plus v is a, but then u7 plus v7 basically is equal to a times u6 minus v times u is 1, right? Therefore we end up with u4. V squared u4 becomes u2 minus 1 plus basically v2 minus v4 plus v6. So we end up with u6 plus v6, u4 plus v4, and u2 plus v2, right? And we have to continue this way to reduce, and then we have to go for find u6 plus v6, and we can find it by writing u6 plus v6 is let's start with u2 plus v2 is u plus v squared minus 2uv, which is a squared minus 1. Okay, and then u4 plus v4 is u2 plus v2 squared minus 2 u2 v2, which is 1. So a squared minus 1 squared minus 2. And then u6 plus v6 is u basically u3, or maybe u2. Let's u2 plus v2 to the third power minus 3 u2 v2, which is 1, u2 plus v2. u2 plus v2 is a2 minus 1 cubed minus 3 a2 minus 1. So u7 plus v7 is a times u6 plus v6. And let's also call a squared minus 1 something like, I don't know, capital Z. And therefore this becomes z squared minus 1. This becomes z cubed minus 3z. Okay? So a times u6 z3 minus 3z minus u4 plus v4 minus z squared plus 1 plus u2 plus v2 minus 1. So the plus 1 and minus 1 cancel out. This becomes a times z cubed minus z squared minus 2z. Okay? So eventually this becomes a times a squared minus 1 times and let's see, we can simplify this further. So take the z out, z squared minus z minus 2, and a plus c here is b. Therefore one of the roots of this quadratic expression is negative 1. Remember, so the coefficient here is 1, the coefficient here is negative 2, and the sum of 2 is negative 1. So a z z plus 1. So one of the roots is minus 1, the other root is so the multiplication is minus 2, so the other root is 2. Okay, so this becomes a squared minus 1, z plus 1 is a squared, and z minus 2 is a squared minus 3. Okay, so x7 plus 1 over x7 is a cubed, a squared minus 1, a squared minus 3. So basically we did a polynomial factorization, right? And then we use our knowledge of the symmetric expression to calculate the final value. All right, question 5. If the a is the cubic root of a plus b plus c is 0, prove that a plus b plus c cubed is 27abc. All right, that's very interesting. If you recall that in problem 3, we proved that a cubed plus b cubed, a cubed, if we have three numbers, let's call it u, v, w. We showed that u cubed plus v cubed plus w cubed minus 3 uvw. 3 uvw. This has a factor of u plus v plus w, right? Times what? Times u squared plus u squared, v squared, w squared minus uv uw minus uv minus uw minus vw. Okay, all right, so all you have to do is so this expression is always true, okay, for any uvw. What happens if we choose u and v and w such that u plus v plus w is 0? If u and v and plus w, u plus v plus w is 0, this term becomes 0, and therefore the right hand side becomes 0. And if the right hand side 0, therefore the left hand side becomes 0. This means that if we have three numbers whose sum is 0, therefore u cubed plus v cubed plus w cubed is always 3uvw. Okay, now simply assume that u is cubic root of a, v is cubic root of b, and w is cubic root of c. Therefore, if I take the raise u and v and w to the third power, I get a plus b plus, because if this happens, then the sum of these three cubic roots is 0, because that's the assumption of the problem. And then we end up with a plus b plus c is 3 cubic root of a, b, c. And simply take the both sides and raise them to the third power. A plus b plus c to the third power is 27abc. Okay, so this is done. And we really didn't have to do anything. Basically, we had to prove the first identity here, u cubed plus v cubed plus w cubed minus 3uvw has a factor of u plus v plus w. Okay? All right, the last question. If 1 over x plus 1 over y plus 1 over z is equal to 1 over x plus y plus z, prove that 1 over x plus 1 over y plus 1 over z to the nth power is equal to the 1 over x to the n plus 1 over y to the n plus 1 over z to the n for any odd integer number. So basically n is 1, 3, 5. I think the problem should have specified that n is positive integer. Okay? All right, how do we do that? Again, I'm going to refer to our one of the problems that we solved in the quadratic section. In the quadratic section, we saw that 1 over x plus 1 over a plus 1 over b equal to 1 over x plus a plus b. We actually solved this, right? We solved this. Here x was the variable and we were looking for x, and a and b, these were parameters, right? We assume that these a and b are fixed and we're looking for x, and we showed that this eventually becomes a quadratic equation, right? Quadratic equation. And I'm going to solve it again. So just remember, we're looking for x in terms of a and b, right? And you can see where I'm going with this. Later on, when we solve this, in order to get the original question, I substitute a with y and substitute b with z, okay? Alright, so 1 over x plus 1 over a plus 1 over b is equal to 1 over x plus a plus b. Now, bring this one to the left side, or maybe let's bring the 1 over x to the right side. Therefore 1 over a plus 1 over b is equal 1 over to x plus a plus b minus 1 over x. We end up with minus a plus b divided by x times x plus a plus b. We're just making a common denominator, okay? And then we multiply, so this side, the left hand side, is also a plus b divided by ab, and therefore x times x plus a plus b is equal minus ab, and therefore x squared plus a plus bx plus ab is 0, and we end up with a quadratic equation, right? Quadratic equation. And we know that the general format of a quadratic equation is x squared minus sx plus p equals to 0. And you can immediately see that the two roots are x equals negative a and x equal negative b, x1, x2. Basically, you can easily see that this quadratic equation can be factored as x plus a times x plus b equals 0. So there are two possible things. So if for this equality to be true, x should be either negative a or negative b. Now in the original problem, this means that if we take x, for example, as the variable and y and z as the parameters, there are only two possibilities. Either x is negative y or x is negative z. There is no other way that the equality 1 over x plus 1 over y plus 1 over z equals 1 over x plus y plus z can be true. One of these two should hold, assuming that the x is variable and y is x is variable and y and z are parameters. Now if this is the case, then 1 over x plus 1 over y plus 1 over z to the nth power is obviously 1 over z to the n, and 1 over x to the n plus 1 over y to the n plus 1 over z to the n is again 1 over z to the n if n is odd. Because if n is odd, 1 over y to the n is minus 1 to the n is x to the n minus 1 over x to the n, okay? The same situation here. So if x is minus z, 1 over x plus 1 over y plus 1 over z to the nth power is 1 over y to the nth power, obviously, and 1 over x to the n plus 1 over y to the n plus 1 over z to the n is equal to 1 over x to the n plus 1 over y to the n plus minus 1 to the n over x to the n, and this is minus 1 because n is an odd integer, and therefore this becomes y to the n. Now obviously there are other cases. For example, if we take y as variable, then we have y either minus x or y either minus z, and if we take z as variable, then we have z equals negative x or z equals negative y. And it's very obvious to show that in these cases also the equality holds. Okay, so that concludes our challenge problems on polynomials. Thank you for your attention.